Hello students, welcome back to this video on bioenergetics part 2. In part 1, I have discussed the definition of bioenergetics and some concepts and definition of thermodynamics. In this part 2, we will discuss the laws of thermodynamics. Many quantitative observations made on the interconversion of various forms of energy have led scientists to the formulation of two fundamental laws of thermodynamics, the first and second. These laws help us understand, number one, the direction of a reaction, whether it will take from left to right or vice versa. Number two, the accomplishment of work, whether useful work would be done or not. And number three, whether the energy for driving a reaction must be delivered from an external source. Now, the first law of thermodynamics. This law is also known as the law of conservation of energy and was first formulated by V. Mayer in 1841 as a result of a study of energy transformation in the inanimate world. But remember, it is equally applicable in living systems. I hope you remember from my video on bioenergetics part 1 that the system means the matter within a defined region and the surroundings refer to everything around the system, and that the system and surroundings make the universe. So this is the system, the surrounding which constitute the universe. Now the first law states that for any physical or chemical reaction in a system, the total amount of energy in the universe remains unchanged or constant. Thus, if some amount of energy increases in the system during the reaction, an equal amount of energy must be lost by the surroundings. So you see, the system either gains the energy from the surroundings or loses to the surroundings. In either case, the sum total of the energy remains the same. Suppose that the energy in the system is E1 and that in the surrounding is E2, and the total energy in the universe is E. Then E is equal to E1 plus E2. However, during the reaction, loss of energy to the surroundings or gain from the surroundings may involve change in the form of energy. So after a chemical reaction, if the system gains the energy by X factors such that the total energy of the system of the reaction will be E1 plus X, and an equal amount of energy will be lost by the surroundings to the system. So the energy in the surroundings after the reaction will be E2 minus that X factor, and the sum of energies in the system and the surroundings after the reaction will be E1 plus X plus E2 minus X, and we know that it is equal to E1 plus E2, and this is equal to E, and E is the energy in the universe. So you have seen that during the reaction, loss of energy to the surroundings or gain from the surroundings may involve change in the form of energy. Thus, the system may lose energy to the surroundings in the form of light or electricity or any other form, but the sum total of their heat equivalents will remain constant in the universe. It can be further explained by taking an example of a chemical reaction. Each compound involved in a chemical reaction contains certain amount of potential energy depending upon the number and kinds of the bonds. When a reaction takes place, these bonds are broken, releasing the free energy. The energy goes to reorganize the bonds and form the products. This bond energy of the reactants and the products is known as their free energies, that is, the energy which is capable of doing work. So in spontaneously occurring reactions, the free energy of reactants is higher than the free energy of the products, and this change in free energy is delta G is very, very important. So if the free energy of the reactant is, for example, GR, and that of the product is GP. So GR is the energy of the reactant and GP is the free energy of the product. And if in the system we have only the reactants with GR as the initial free energy and the products with the final free energy GP at equilibrium, then the difference between the final energy and the initial energy will give the free energy change, that is delta G. So delta G is equal to GP minus GR. If in such a system GR is greater than GP, then delta G or the change in free energy will be negative and will favor the spontaneous reaction. In such a reaction, the system at the end has lesser free energy by an amount, the negative delta G value. This energy is dissipated in the form of heat and goes to the universe. Remember, the bond energy here has been converted to heat energy and has moved out of the system to the surroundings. But the total energy content of the universe remains the same, although in changed form. Such reactions are said to be exergonic and will occur spontaneously because they do not require any extra energy. So if GP is more than GR, delta G will be positive. In such a situation, the free energy of the product is more and the reactants are not able to meet it on their own. Such reactions are said to be endergonic and will not occur spontaneously. They will, however, occur in the desired direction when additional energy is made available. So I hope now you have understood the first law, that the energy is neither being lost nor gained. It simply changes form and keeps on shifting between the system and the surroundings. Thus, the energy is neither created nor destroyed. So now we come to the second law of thermodynamics. The first law of thermodynamics cannot be used to predict whether a reaction can occur spontaneously. The universe has a tendency towards increasing disorder, and in all natural processes, the randomness or the disorder of the universe means system and surroundings, increases. So what is the second law? The second law states that at each transfer or transformation of energy, part of that energy assumes a form that cannot be passed on any further because it is randomly dispersed, often as heat. And it is this randomly dispersed energy which is called entropy. So ultimately, closed systems run down, but open systems such as ecosystems, however, with their constant input and outflow, maintain a steady state in spite of the second law of thermodynamics. Biological systems thus do not seem to conform to the second law, for the tendency of life is to produce order out of disorder, to decrease rather than increase entropy. And in 1878, Gibbs created the free energy function by combining the first and second laws of thermodynamics in the form of this equation, that is delta G is equal to delta H minus T delta S. Delta G is the change in free energy of the reacting system, delta H is the change in enthalpy or the heat content of the system, T is the absolute temperature at which the process is taking place, and delta S the change in entropy. Entropy means disorderliness or randomness of this system. Now delta G is a valuable criterion in determining whether a reaction can occur spontaneously or not. So if delta G is negative, reaction proceeds spontaneously with loss of free energy, that is exergonic. In addition, if delta G is of high magnitude, the reaction goes virtually to completion and is essentially irreversible. But if delta G is positive, reaction proceeds only if free energy can be gained, that is endergonic. So if delta G is of high magnitude, the system is stable with little or no tendency for a reaction to occur. And in the situation when delta G is 0, the reaction system is at equilibrium and there is no net change taking place. The delta G of a reaction depends only on the free energy of the products minus that of reactants. So it is very important to know that the delta G of a reaction is independent of the path of transformation. Another important point is that the value of delta G provides no information about the rate of a reaction. So negative delta G indicates that a reaction can occur spontaneously, but it does not signify that it will occur at a perceptible rate. Besides that, there are two more technical terms, delta G naught or delta G0. It is the free energy change under standard conditions. So it may be defined as the difference between the free energy content of the reactants and that of the products under standard conditions. So what are the standard conditions? Temperature 25 degrees Celsius or 298 Kelvin, pressure 1 atmosphere, and concentration of the reactants and products are 1 molar. And delta G naught dash is dash, or rather delta G naught prime, is the standard free energy change at biological pH, that is pH 7. The first law is concerned with the accounting of the various kinds of energy involved in a given process, and the second law is concerned with the availability of the energy of a given system for doing useful work. Thank you.